Welcome to the Week 6 lecture for microprocessors and robotics. This week we'll be looking at a couple of new mnemonics that you're going to be using in your programs for Lab 3. And so naturally we'll also go over Lab 3, what that entails, and then what we'll spend the majority of our time reviewing this week is the first phase of your project, which is the brainstorming phase. So there's a couple activities associated with that. The project is spread out over the course of the semester. So instead of just giving you a due date and requirements, we work through different steps of the project, different weeks throughout the semester. This just helps keep an even pace so that you're not rushing to get everything done last minute, and it's a good way to perform some checks as you go through the process so that I can help you verify this is a good project, you're on track, and your peers can also help provide input. Before we get into the new commands this week, I want to review the virtual architecture associated with the compiler online that we've been using, that demo.yasp. And we need to go over this because the commands that we're using will relate to these pin numbers. So you just need to know which pin numbers control which components. And also when we start using our Arduino boards, it will be the same thing. Certain pins will be associated to certain components that are connected. So what is pin 5 on here may not be pin 5 on your Arduino board. It can be a little bit different depending on which microcontroller you're using, but right now we'll just look at the specifics of this virtual microcontroller. So you can see here I have all of the pins laid out for you in a list on the right, or all of the relevant pins. And then you can see on the left here where it says pin 5, right here. So when you bring up your compiler, if you hover over any component on the board that is assigned a pin number, it will display that pin number for you. So if you hover over this green LED, it will display pin 5. If you hover over the yellow LED, it will display pin 4. I'm going backwards here. So if I start at the top with pin number 1, that would be the gray button. Let me highlight that here. It should be pretty obvious, but that's the gray button right here. Pin number 2 is connected to the red button, and so you can actually push these buttons when you run your code to test it. So we won't be using the buttons in our lab, but I just want to outline that is what the pin numbers for those are. Pin 3 is associated to this red LED. It's a little bit hard to tell the color since it's not lit up, but that is a red LED. And pin 4 is yellow, and pin 5 is the green LED. So you can refer back to this as you're programming, or what's probably simpler is to just hover over these LEDs as you're programming, and that will help remind yourself of the pin numbers associated with those. Moving on to our new commands this week. This week we only have 3 new commands to use, and you'll see why when we review the lab. But essentially this week we're going to spend part of our time focusing on changing codes to be competitive with different microcontrollers and different architectures. Then the other half of this week will be spent with these new commands, in addition to your project phase 1. So we have essentially a lot of little pieces going on this week. So we're not getting too far into any one thing, but rather we're getting into a lot of things a little bit this week. So the first command that we're going to look at is the high command. And what this does is it turns a pin on. So typically pins are in what we call a high or low state. They're set to 0 or 1 when we use binary. And 0 reflects a low state, and high would be a 1. A 1 reflects a high state. So if a pin is high, it will be on, and it will activate whatever is attached to that pin. So if an LED is attached to that pin, the LED will light up. If there is a speaker attached to that pin, some sound could be emitted. It can be a variety of things. But when a pin is high, it will trigger whatever is connected to that pin. Likewise, if a pin is set to low, anything connected to it will be turned off. And we also have the toggle command. So this can turn a pin on or off depending on its current state. So what toggle does is essentially it just switches back and forth. If your pin is low, and you use the toggle command, it will turn your pin high or on. If your pin or your LED or whatever is connected to it is on or in a high state and you use the toggle command, it will then turn it off. So we use high and low when we want to be real specific about what we want our pin to do. And in some cases, we may just need to toggle the pin back and forth to the opposite state. So now we can take a look at how do we use these in a code. Well, it's actually really simple, at least with this compiler. So all we really have to do is write the command. So this first one I have high, and then we just put the pin number after it. So note, this is not a traditional number like we would use when we're adding or when we are moving numbers, right? Then we're using decimal numbers for that, and those are representing a value. In this case, these numbers are representing pins. So here, if we say high 5, this is going to turn pin 5 on, and this pin 5 is connected to a green LED, if you'll remember. Likewise, same thing for low. We just put in low, a space, and then the pin number, which in this case is 5, so it would turn the green LED off. And then same thing for the toggle command. All we have to do is write the command and the pin number after it. So in this case, if our LED was off from this low command, and then we use the toggle command, it would turn the LED back on. And so that's how we use these commands. They're pretty simple and straightforward. When you're turning pins on and off, all you have to do is use one of these commands and then put the correct pin number after it. Move on to discussing program editing. What do I mean by program editing? Of course, as you're building your program, you're probably editing it and changing things. But what I mean here is when you have a combination of your programming language and a computer architecture, that gives you a complete system. So in week 3, we talked about how assembly or any programming language is generally used across the board. There are a lot of similarities. It's recognized as a separate language, but the computer architecture can change the nuances of how we program with that language. And so that's how we get a unique, complete system. And the comparison that I gave for that was like if you think about a language as your programming language, and the modifier is the country in which it's spoken, just like our computer architecture is the modifier for our programming language. So a language in one country may sound very different than the same language in another country. If you think about how English is spoken in the US versus the UK, or versus a lot of countries have English as a secondary language, and it probably sounds a little bit different. There's different accents. Sometimes there can be a little twist on words that are even a little bit different. It's all English, but there's some nuances there. So it's the same thing when we're working in assembly language. Depending on your system, there are some nuances to the code that you may need to change some things to get it to work with a different architecture. So what I want to do is go through an exercise of having you be able to recognize what you need to change to get an assembly program to work with a different architecture. So what I have pulled in here is actually a program for a different microcontroller than what you're working with, or the compiler that you've been working with. This program is for an MSP430 microcontroller, and this is built in Code Composer. So this is still assembly language, but you can see it's a little bit different. And so what you're going to do as part of your lab assignment is go through one of these programs and correct all of these differences. So very quickly, I'll just point out a couple of things. And the nice thing about using the YASP compiler is that when you hover over the X, it will give you a clue as to what could be wrong with the line of code. So we see up here on line 6, we can't hover over the X in this mode, but this is probably extra and we don't need it. So we can probably delete a lot of this stuff in the top. Some of this stuff, you might notice that the register numbers are a little bit different. We usually use B as a register number. This code is using memory locations, which we don't have access to in this particular compiler. So if we were correcting this code, what we might need to do is change from a memory location to a different register. So that would be an appropriate solution. The structure of the commands may be a little bit different. So here in this case, on line 30, we have a number and then the register. So that may be the correct format, or you may need to change that to get that to work in this compiler. Just something to be aware of. Some other commands may be misspelled, they may be out of place, or written just a little bit differently. So in your lab assignment, you will need to look out for anything that may need changed or tweaked a little bit to get this code running in the compiler that we're using. So I just outlined several things that you'll want to keep an eye on when you're editing a program, or really in any case if you're switching from one architecture or compiler to another. But here's just a concrete list of things for you to check for as you're going through the code. And again, the compiler that we're using, when that X shows up on the left, it will sort of prompt you as to what's wrong with that line. But you should be aware of some of these potential issues that could occur when you're switching architectures. So the first of those is setup information. So you might have noticed in the last slide there was a lot of stuff at the beginning before we had the main program. So some controllers require a lot of setup commands. They have to pull in libraries, or just depending on how the compiler's set up, it might automatically pull in these libraries. And so when we use that with different architecture or a different compiler, it may not have those same libraries. So we may need to either edit our setup information, or we may need to delete any extra setup information that's not relevant. Some of the register and memory locations may need changed. I mentioned this, the code that we just looked at uses memory locations. And in the YASP compiler, we don't have access to memory locations, so we would want to change those to be a register. You'll also notice that the registers were written a little bit differently. They may need to be reformatted to match the correct register format of the architecture or compiler that you're using. And that's really a common one. Typically, register formats are not the same between architectures. We know we're always referencing a register, but what that register's name is may vary between your systems. You should also pay attention to the number system being used. So other systems may require formatting in different number systems. Also look at the command syntax differences. So a couple weeks ago when we looked at our end command, we saw that we use the END to end our program, but sometimes in some architectures or some systems, NOP is also used to end the program. Sometimes those are interchangeable and sometimes they're not. So that's something to look out for. Commands may vary just a little bit in how they're written. Besides architecture-based checks, there's also a few proofreading checks to be aware of, and you may have already encountered these in building your own codes, but just a reminder, when you're editing somebody else's code, or even if you are testing a code off the internet and you're making changes to it, you may need to do some proofreading. So proofreading checks include misspellings. Commands could be simply misspelled, and that could be what's tripping you up. There may not be a syntax difference, but it just may be a spelling difference or a misspelling. There may also be incorrect numbers being used. If you accidentally hit a 5 instead of a 6, just make sure all of your registers and values are correct as you're reading through. And your commands, always remember that they need to be indicated with a semicolon. So that's what we're using in our YASP compiler. Sometimes in other compilers, commands can be indicated with a double slash. That's what sets a command apart. And so that's something to also pay attention to, is to make sure your commands are properly separated out from the rest of the program. Now we'll move on to a quick look at the instructions for Lab 3.0. We've already covered most of this, but I will review these instructions real quick. So the objective of this lab, we really have two objectives here. That's why I said we're working on multiple things this week. Your first objective is to be able to revise an assembly program that was written for another system to work with the system that we're using. So it's still assembly code, still assembly program, but it may just need a couple tweaks to run with the compiler that we're using. And so a really important part of programming is being able to recognize what needs changed or being able to pick up somebody else's code. So that's the first objective for this week. The second objective is to be able to use our new commands, high, low, and toggle, to control those LED pins that are on your virtual microcontroller. So part one, I've given you a program in the lab. I have not copied it all into this PowerPoint, but when you download Lab 3.0, you'll be able to see it. So what you want to do is copy that program into your YASP compiler and correct all the errors so that you're able to run the code. And just looking at the code, it should be pretty obvious what it does. I'm not going to tell you simply because that can be part of picking up somebody else's code, is you have to figure out what it's doing. There's not always a nice, neat little summary. But this is why comments are so important too, is because if somebody else has to pick up your code and there are no comments, it's going to take a lot more work for them to figure out what it's doing. So you'll want to go through all of that and correct all of those issues. And then I'm asking you to go ahead and get rid of the code that's in the lab. You can delete it from the lab report. I don't need to see it. I already know what code I've given you. But what you do need to do is put in your code that you've corrected. So you can just do a copy and paste from the compiler so that you're pasting in text. That's perfectly fine. Or if you want to take a screenshot of your code and put in the picture into your lab document, that's also perfectly fine. Next, we have part two, which relates to our second objective of being able to use our new commands to program LEDs that are attached to our virtual pins. So the first thing that you're going to do is build a code that turns on the green, yellow, and red LEDs in that order, and then turns them off in the reverse order. So you'll turn on the green, then the yellow, then the red, and then you will turn off the red, turn off the yellow, and turn off the green. So you'll go through and build a program that does that one time. And just like part one, you'll include your code, again, either as text or a screenshot. Either one is fine, and that applies to essentially all of your labs. The second part of part two is changing your program to blink each LED. So you're going to turn an LED on and then turn it back off right away. And you can do that in any order. The last part is you don't have to paste in your code for part C. You do have to include your code for part B. I've said that here in the instructions. But for part C, I'm just asking you to explain to me what would you change in your program to get your code to repeat 4 times. And I've given you a little hint there. And then lastly, same as the previous 2 labs, I'm just asking you for a short paragraph. It should be around 3 to 6 sentences on any observations that you've made in this lab. So what is happening and how does that relate to the course concepts that we've reviewed? Now we're going to talk about project requirements a little bit. So your final project, you're going to choose something that uses the concepts that you've learned in this course. And of course, you haven't learned all of the concepts yet. So you won't actually start this assignment until next week, but I want to cover it this week so you can start thinking about it. Next week, we'll get into using our Arduino Uno board, and so you'll get more of an introduction to that. But these are good parameters to have in mind as you start getting introduced to your Arduino board. You can start thinking about your project and about what you might want to do. So what you'll do is you will construct a project based on something you can do with a microcontroller. So in the past, I've had students come up with a really complex blinking array of LEDs. They've done a water sensor. So the sensor determines the water level or if the water hits a certain level, and then that triggers an alarm in the form of an LED. Some students have connected a speaker to their microcontroller and they've programmed it to play some music. So there's a whole variety of things you can do. I will be giving you some additional ideas, and Google is also a really good tool. You can see what sort of projects others have done for inspiration. The huge advantage of using these Arduino Uno boards is that they're so common. So a lot of people have done a lot of these things, and you'll have a lot of reference material to draw from. So you'll be coming up with a project, and then you'll just do a short little demo of your project and then do a project report. So your project report will tell me what was your main goal, what did you set out to accomplish, essentially. And we'll cover these more in depth when we get closer to the end of the semester when you're writing this final project report. But just to give you an idea of the scope, you'll be talking about your main goals, how you brainstormed ideas for your project, what were your deliverables, what were you hoping to accomplish, and what were the steps that you took along the way. We'll be doing a risk assessment later on in the semester. You will be planning out your timeline, and you'll speak to that timeline and how well it was executed. You'll talk about your progress in the project and any issues that you had, the results, of course, that you got at the end, and then what your recommendations are for potential improvements to the project. If you had more time, if you had more resources, what else could you have done? And then, of course, references. So I will cover all of those sections more in depth towards the end of the semester when you'll actually be writing your final project. But I want to cover this from kind of a 5,000-foot view now so that you can be thinking about your project as we start looking at the UNO boards next week, and even the assembly programming that we've done this week and your work turning the LEDs on and off. You can kind of get the wheels turning and start thinking about projects that might be interesting to you. Now let's get into some of the basic project steps that you'll see as we go through this process. So most projects have these 5 basic steps, this is the steps in their simplest form. Each step is not necessarily basic or simple, but every project has these steps. And so the first step is initiating the project. You're figuring out, what do you want to do? Why are we doing this project? And you're determining that on the initiation phase. In the planning phase, that's where you're figuring out, okay, how do we do this project? So first it's a what, then it's sort of a how. And you're mapping out your resources and what you need and what your timeline might look like. And then, of course, when people think of a project, what they probably think of most often is the executing stage. This is where you're actually getting stuff done. And this is where you'll be carrying out your sort of experiments, trying out your programs, trying out your code, all of your construction that will go into this, your troubleshooting that in this process. After executing, you'll go through a monitoring and controlling phase. And we won't be in this one as much with this particular project, but in most projects you would then monitor your results, make sure that they're what you need, and then make sure that they're acting in a controlled manner, so nothing wildly crazy is happening. So I said we won't be doing much monitoring. You probably won't be leaving your system to run over a weekend or anything crazy like that, but you'll probably be doing monitoring for a brief amount of time, right? You will monitor your complete system to make sure it's functioning how you expect it to. And that could be for a minute, it could be for 5 minutes, 10 minutes, just depending on the nature of your project, but essentially there will be a monitoring and controlling phase. And then we come to the closing phase. And this closing phase is documenting or pulling together all of your documentation. This is essentially showing people, here's what I've done. Here's why we did it. Here's how we did it. And here's what happened. And here's why it's a good thing. So you're covering all of this in your closing phase. For you, this will mean completing your final project report. All of that information that you've gathered in all of the 4 previous phases will be culminated in your final report in the closing phase. Getting into the project steps in a little bit more of a detailed view for this project, the first thing that we'll do starting next week is we will start brainstorming ideas. So essentially anything you can think of, we're going to brainstorm a whole big list of ideas, potentially bounce them off of each other. Then after this step, you'll go on to research your ideas. So you'll develop them, you'll get a better idea of what each one entails. In brainstorming, we don't fully flesh out each idea. We just write it down as an idea. It has potential. Then when we research, we're exploring that idea more in depth. We're saying, what do we need for this? Do we feel like we have the capacity for this? Is this within the scope of the course? What would I need to complete this project? So that's where you're researching and gathering more information about your ideas and what it would take to accomplish them. The third step is quite simple. You'll just select an idea. And so when we get to this step, again, you will be getting input from your peers. We'll set that up in the discussion boards. And then I will also be giving you input. So you'll be submitting your brainstorm ideas to me. We have a little sheet that we fill out and a couple other ones. So the good thing about that is when you submit those sheets, I get to have a quick look at your ideas. I know what you're thinking about doing for your project, and then I can provide some input. I can let you know if it maybe seems too simple, if it would be too complex for this course, if maybe it's close, but there would be a modification that I would suggest, or if it's just right. And so I can give you a little bit of input and guidance as to which idea to select. After this, you're going to do more research and develop your idea a little bit further and figure out exactly what you need to perform this. You'll probably come up with a timeline and you'll figure out all the details of turning this idea into a full-fledged project. Then in the next step, you will be constructing your project. You'll be making it happen. And then if any issues come up, of course, you'll troubleshoot those, figure out what's wrong, correct any errors, and continue on until hopefully you have a working project. Then lastly, we get to that closing documentation phase where you'll write a project report. It will include essentially a narrative of all of the steps that you've gone through. You'll tell me all about your project, how it went, and what the outcome was in this report. So after I've paired you up into teams, you'll all jump in and start the brainstorming process. So what is brainstorming? Let's take a look at that in a little bit more detail. So brainstorming is how we arrive at creative ideas, right? They don't just pop into our heads. Sometimes we need to take time to brainstorm ideas and solutions, and sometimes you can come up with these if on your own time. It can be a little bit easier. When you're working in a group, specific brainstorming sessions can really help to guide the brainstorming and keep everyone on the same page. So we'll be using a couple different tactics to brainstorm, and in these, of course, every single team member is encouraged to, well, think or type your comments, right? Thinking out loud, typically, if you're all together, just wandering, you don't really have to filter your thoughts. As far as ideas, maybe I should say that you don't have to filter your ideas. Just anything that comes into your mind as a potential, throw it out there. So when you're brainstorming, it's very important to say there's no analysis of your ideas. Don't second guess it or say, oh, nope, this would never work. You don't have to discuss it in depth. Don't criticize other ideas. These steps are important to the process, right? Because not all ideas are good ideas, but this only happens when the brainstorming session is over. So the brainstorming session should be about getting out as many ideas as possible. And then we would move into an evaluation session where you look at all of those ideas and then you start to analyze them and talk about them and look at the pros and cons and say, okay, we have all of these ideas from our brainstorming session. Which ones are the best ones? So brainstorming is just getting all of your ideas and possible solutions or possible projects, just get them out there. So to help facilitate brainstorming and less evaluation, there's a couple really good guidelines that you can keep in mind when you are brainstorming. The first is to focus on clear goals. So what is the outcome? If everyone is brainstorming on how to accomplish how to build a car and somebody else is brainstorming on how to build a scooter, those ideas are not going to come together real well. So make sure that you're all focusing on the same goal. It's also important, as I mentioned before, nothing critical in the brainstorming phase, don't evaluate your ideas and decide if they're good or bad in the brainstorming phase. If it's an idea, throw it out there. You can always start on your own. Sometimes we can just keep going in our own head, but it's also a good idea to get them out there. That's I'm skipping down to point 9 a little bit. Record everything. So any idea, write it down. Going back up to number 5, quantity over quality to an extent. So when you're brainstorming, the more ideas, the better, even if they're a little bit out there. That's perfectly fine. You can always discard those in your evaluation stage, or there might be a wild idea that could work, or a piece of a wild idea that you could tone down and integrate. So sometimes it's good to be off the wall, and brainstorming is the place to do that. You can also build off of the ideas of others. If somebody throws one idea out, you can take that idea and say, oh, what if we did that, but we also added this? So you can build off of each other's ideas. And then typically there would be a facilitator to help keep the group on track and to ask, okay, guys, what else can we think of? Is there anything else that we can think of? And typically, in a in-person session, a facilitator is more important. I think if you set up a video meeting, a facilitator will still be important. But if you're doing like a discussion post type format and going back and forth, you may not need a facilitator as much. And then, as I said before, it's very important to get all of your ideas out, especially in this format, write everything down for everyone else to see, just get your ideas out there. So just because brainstorming is about getting all of your ideas out, that doesn't mean it has to be a chaotic process. So we'll go ahead and take a look at a couple of different techniques that you can use when you're brainstorming. The first one shown here is a mind map brainstorm, or what might be called a cluster brainstorm. And so in the middle, we have all of our ideas. And you can see we're thinking about bioluminescence, we're thinking about cooling, maybe a pH detector. We're thinking about all these different project ideas. One thing can lead to another. So if we're thinking about cooling, we might also, if we're thinking about cooling, we also might be thinking about heat absorbing proteins. That might make us think about heat shock. So when something makes you think of something else, you're connecting things with these little lines. So you're kind of creating a web of ideas. So you might have, looks like we have 1, 2, 3, 4, 5, 6 main ideas spinning off this central hub here. And then from each of these, we've branched into other thoughts. So protecting wood has made us think about killing termites. If we kill termites, is there going to be any poison involved? And so on. So you can tell this is kind of an interesting mind map that we have here. But yours would be similar in that you would start with your central idea, a project, and then you might come up with a couple ideas like water level, and then off of that you could say high water levels or dam water levels, or you could branch off into songs or music. Music could come over here and be one branch. A song could come over here and be one branch off of this one. You could have multiple possible songs to make your microcontroller play. And so you're just building ideas off of each other in your mind map and connecting them all with these little webs. Another and really simple method for brainstorming is the ideas method. So here you can see there's only 3 steps. So the first step is generating ideas. Essentially, this would just be a really long list, ideally, of potential ideas. And then you would group those ideas together by similar things. So if there were a lot of different ideas about making a mini robot, right? Maybe people had some different ideas on robots or different ideas on the types or what they would do. You could group all of those ideas into one group. And so group similar ideas together after you make your list, and then you're simply reviewing your list. What are the common themes in your brainstorming? Then you kind of get into the evaluation phase. So here, pretty simple, make a list, group like things together, and see what categories you come up with. A third method of brainstorming is storyboarding. So here you're essentially drawing out what would happen, right? So if we did this, what would happen next, and then what would happen. And so you're kind of drawing out a sequence of pictures that depict the possibilities. So if you're a really visual person, this might be a good way to see your brainstorming ideas instead of just writing a list or instead of mapping everything together. It might be really useful to kind of do this story, this picture format here. And so here you could do one scene for each idea. You could do multiple scenes for each ideas, but essentially you're drawing out your ideas onto a storyboard as you brainstorm. The last type of brainstorming that we're going to talk about is wish lists. And so typically when you're wish list brainstorming, you start out with a really wild idea, right? So think if you could do absolutely anything with this project, if you had all the time and resources in the world, what would you want to do? And then we would go and pare that down and say, what makes this so impossible? Why can't I do this? What are our constraints? And then we say, okay, how can I work inside those constraints? Which features can maybe go? What is the essence of this big wish? And so you can strip a really large, time-consuming project down into something that is more manageable, but you're still starting out with a really great idea by a wish list form. So you can still come up with those novel ideas and then you compare them down to make them more reasonable. So I've included this slide to give you an idea of some of your available resources. So I've had the university purchase a couple of these kits that contains all sorts of things to give you ideas for your project, and you can certainly, I encourage you to use these components in your project. And of course, you can research and see how can you use these components, what are some different projects that you can do with a Launchpad. I absolutely encourage that. Look it up and see what other people have done to inspire yourself. So some of the components that you can use, you'll see there's a joystick in these kits. There are membrane switches where you can input numbers and some letters. We have different colors of lights. There's a laser emitter. We have tilt switches. So if you're bored, if your microcontroller is mounted to a board, the tilt switch will sense if the board is tilting, which could trigger something else to happen. There's a photoresistor that will sense the presence or absence of light. So you could integrate light sensing into your project. There's buttons, buzzers. Let's see, what else do we have? We have a sound output board. As I mentioned before, in previous courses, some of my students use the big sound output board to essentially create a Christmas song, to get a Christmas song to play with their board. They were able to program that. You can see there's a board for the digital temperature, there's a magnetic springboard, water level sensor, ultrasonic sensor. So you have a lot of options in these kits. If you want to, you can certainly purchase additional components, but I've tried to get a couple of these kits so that you have everything you need. And so I would encourage you at some point in the semester as you're working on this project, you don't have to worry about it now for brainstorming, but later on, I would encourage you to take some time to look into these kits and kind of play with the components. These are all at the Kent Tusk campus. You can find these. The lab technicians can help direct you to them. And these are all available for you to use as long as you return them. So hopefully you can take a look at this list, do some research, see what other people have done. This will provide some inspiration for your project. So for assignments this week, you have your lab report 3.0. That'll be due this next Sunday at 11:59 as usual. And then for your team formation and brainstorming session, again, because I know this can take a little while online, I've given you 2 weeks to complete this. So I recommend not wasting a week before you start this. Certainly try to get going and start it this week. That way everyone in your team has plenty of time to react and respond, and you can all select the brainstorming methods and go back and forth and select the top ideas. So you have 2 weeks before your team formation and brainstorming sheet is due. And that is it for the lecture for week 6.